Hi class. This last part of Chapter 3 talks about science and what is science, what is a scientific theory, and what makes science different from other ways of acquiring knowledge. To define science, it's kind of difficult. You have to really just kind of think about the process that a scientist or groups of scientists would go through to explain something in nature. So we explain things that we can observe, and we try to develop models to explain what we observe and then make predictions about tests, experiments that you can do. So that's scientific knowledge. It comes from those experiments. Then there's, of course, other knowledge in the world, knowledge about, the foods you like. For example, you like apples instead of oranges. That's knowledge, but, it's not necessarily scientific. It's just a fact that you like apples, more than oranges. So not all knowledge comes from science, but the knowledge we acquire from science is acquired in a fairly precise way, in a way at least that is it can be predictable eventually. So here's a method, kind of it's called the scientific method, but it's really more of a process, and it isn't necessarily followed step by step in a precise way. But the general idea is that you make an observation of something that you see in nature, like the moon maybe having these phases, and you say, well, why is that? Why is that happening? And you make a suggestion. You say, well, I think it's happening because the Earth is casting a shadow on the moon, and the shadow makes the moon look like a different shape throughout at different times of the month. So you make that guess, you make that hypothesis, and then you make a prediction based on that. You say, well, all right, because of that, I think that in 2 weeks the moon is going to look like this, or after a few months, this is going to happen, or because of what you're thinking is the reason why something is happening, you can make predictions about what will happen in the future. So then you do an experiment and you test that prediction. And the experiment could just be simply another observation, or in the case of maybe testing things about atoms and molecules, maybe you do an experiment in a laboratory and you do some tests with them. You make them colder, you make them hotter, you shine certain light on them, and you make predictions about what will happen, and you test those predictions. So that is really the big part of what science is. It's about testing the predictions, not simply guessing what's going on, not simply making an educated guess, a hypothesis, but testing that educated guess and testing it over and over and over again. So if you perform a test on a hypothesis and your test disagrees with your prediction, then you have to go back up and you have to revise your hypothesis. You can't just simply say, oh, okay, yeah, my hypothesis is fine. No, you have to go back up and you have to modify it. You have to change it, and you have to, figure out, okay, what's if it's not the Earth casting shadows on the moon, then what else could it be? And you think about other reasons why you observe what you are observing, and then you make more predictions and you make more tests, and if the test agrees with your prediction, then you go back up and you don't necessarily say, okay, my hypothesis is correct. You don't say that. You say, well, okay, let's make another prediction and let's test that again. You keep doing this process over and over again, and never in the process of science do you ever prove that your hypothesis is correct. You might make thousands of predictions that all test correctly, and the experiments agree with your predictions, but that still does not prove that your hypothesis is correct. What it does is it makes your hypothesis more of what we call a scientific theory, that it's been sort of validated over and over again, but we can never prove a theory is correct. And a theory, we'll see this again in a minute here, but a theory is not just a guess. A theory is a very well-tested hypothesis. It's more than a hypothesis. It started out as a hypothesis, but it's been very, very tested, and not a single experiment has ever been done to discredit it, to disprove it. But a theory is always something that could be disproven. It could be falsified, as we say. And so scientific theories are things that can be falsified, that can be proven wrong, but we can actually never prove them correct. So we never do this process really step by step the way we had outlined there. Different groups of scientists do different pieces of it. Some people are experimentalists, some people are theoreticians, and they do more of the mathematics. Sometimes you start with an observation. Sometimes you might start with a hypothesis, because maybe not because you observe something, but because you think that something might be happening for some other reason. And so you make a hypothesis, and then you go ahead and do some experiments and make observations and see if your hypothesis is valid in any way. So there's a variety of ways to get into this process that we call science. And we're going to talk about a couple different sort of what we call hallmarks of science. And the main thing that science tries to do is it tries to explain things about nature, things that are based on natural causes, we say. Science doesn't address issues concerning supernatural causes, divine intervention. This doesn't mean that science says that there can't be divine intervention. The scientific model just doesn't include that as in part of the process. And we can't say, as a scientist, you can't say, well, we can't quite explain this, so we're just going to leave it up to divine intervention. That's just not the way science works. And so you just try to keep explaining things based on natural causes. And and there's a lot of successful explanations of things. And this doesn't mean, again, that science is trying to disprove the existence of something supernatural, a God, but it also doesn't mean that science can verify that there is a God. So science is really, we want to try to keep science, operating in a certain way so that it's consistent and it's understood by people, and it's agreed upon by people in terms of what it's predicting. And there's in reality there's always disagreements, and scientific theories that have been verified for years, hundreds of years, still have people that disagree with them, and they're still looking for ways to disprove the theories or the hypotheses. So science, a scientific theory doesn't mean that everybody always agrees with it. It means that there are always people that are questioning. There's always questions, regardless of what it is you're talking about. Einstein's theory of relativity is a very well-established theory that has never had a single experiment done that has disagreed with it. But, there are still people that question it, and that's good. That's part of what science does. There's all kinds of different things. You look at climate change, global warming. There's people that lean in one direction on the truth of it, the extent of it, and there are others that lean in a different direction. And they all have different pieces of evidence for their view. And that's good. That kind of debate is a good thing. You never want to shut that kind of debate down in any scientific theory. So what we do then in science is we have models. We start off with a model of why something happens. And, for example, Copernicus's model of planets going around the sun rather than everything going around the Earth. That was a model. We try to simplify it, and Copernicus did simplify the model. If you think back to Ptolemy's model of all the circles upon circles to try to explain the motion of planets, well, Copernicus's model was much simpler. It was simply circular orbits of planets going around the sun. But he did have to add a little bit of circles upon circles as well, but not as much. It was certainly not as complicated as Ptolemy's model. And so the idea is that it's usually the case that the simpler the model, the more correct it is. And so that's what scientists also try to do, is they try to look for models of nature that are simple. And that was a big thing that Einstein did, is people were having all kinds of issues with light and the speed of light and the equations of electricity and magnetism, and some assumptions that they made about how light travels. And people were having difficulty explaining different things. And Einstein backed up and said, well, wait, let's simplify this, and let's make this basic assumption about light and how it travels through space, the fact that it doesn't need any medium, any material to travel through. He said, let's just make this assumption and see where it leads. And he was just brilliant in his ability to come up with little experiments that you could do, kind of in your mind in a sense, as to what the consequences would be of that simplifying assumption. And ultimately, people then did real experiments and showed that in fact he was correct as far as we can tell. His assumption is valid, and the whole theory of relativity stands on a very strong footing right now because of all the experiments that have been done over the last 115 years, 110 years or so. And then a scientific model, a scientific theory, hypothesis, whatever stage it's at, it has to be testable. You have to be able to make predictions from it and test those predictions. You can't just simply say, like astrologers might say, on this day, watch out for a black cat. Well, that doesn't do anything. I mean, so you have to be able to test it. And so, of course, then you have to say, okay, well, let's go find a black cat and see what happens. So you go test it, and you see if anything happens. And, usually the astrological predictions don't really tell you specifically what's going to happen. but it just tells you to watch out for something, or on this day you might get something special happening, or whatever. You always want to test these things, and that's what science is all about, is testing hypotheses, testing the predictions that you can make from hypotheses. So a scientific theory, we've said some of these things already. The scientific theory is not the same as a hypothesis, but it's really it's kind of a hypothesis that's been modified over and over and over again based on experimental tests, and it has sort of withstood the test of time over and over again. Nothing has disagreed with it. At least, there might have been some very minor disagreements which cause you to modify it slightly, but the scientific theory is very solid in how it explains something that's going on. So Einstein's theory of relativity explains what happens when things move at speeds close to the speed of light, how we measure different things differently, length and time and so on. His general theory of relativity explains gravity, and how we can explain what happens with gravity when we're near things like black holes and stuff like that. So all these predictions that those theories have allowed us to make have been tested, and there are probably other ones out there that haven't been tested, but people are working on different tests of these theories to make sure that they're strong as they can be. And the word theory in everyday life is very different from the way we use it in science. In everyday life, people will say, "Oh, I have a theory as to why the Cubs are going to win the World Series this year." Well, that's really just a hypothesis. That's not a theory. You're just making a guess. You're just throwing out some opinion. That's not a scientific theory. Scientific theory is a very solid understanding of nature. So other words as well in everyday language have different meanings, and your book has a good table of several of these words here as to what they mean in terms of a scientific understanding of them versus a kind of a layman's term sort of understanding, the everyday sort of understanding of the words: bias, model, hypothesis, uncertainty, and so on. Error, in science, for example, uncertainty doesn't necessarily mean that you don't know something about something, but rather it means that you've made some measurements, and your measurements, aren't perfectly precise. There's a little bit of, plus or minus kind of numbers in there. So you might measure a distance, and you might measure that distance to be 2.5 meters. But that 0.5 meters, that half meter, might have a little bit of sort of fuzziness in it, because your measuring device isn't perfect. So you might say 2.5 meters plus or minus 0.1 meter, just to indicate the fact that your measuring device is not perfect. That plus or minus 0.1 meter is what we call your uncertainty in that measurement. So other words have other meanings as well, but in science we try to have very precise meanings for the words that we use, so everybody knows what we're talking about as we talk to one another. So astrology, then, I kind of briefly talked about astrology, but astrology, of course, looks for sort of hidden influences on people, on their lives, based on the positions of planets and stars and the moon and the sun and the sky. And of course, you can test these things, but it's a little bit more difficult, because often you look at horoscopes and the predictions are not really very specific. They're not necessarily always testable. But if you find one that does make a prediction, like such and such will happen today, yeah, you could go back and think, okay, did that actually happen today? And most likely it didn't. So, in fact, if you were to do a kind of a scientific study of the success of astrological predictions, you find that they're really they're no better than just random chance. So if predictions, you're going to find that your horoscope says that on this day something's going to happen, and it does happen. That'll certainly happen, but it's no better. It won't happen any more frequently than just pure chance, like flipping a coin. So that's very different from science, where in science, when you make a prediction, that prediction must come true. Otherwise, your hypothesis, your theory that prediction is based on, has to be modified. So that's the main gist of the last section of this chapter, of Chapter 3. But I urge you to read about the scientific process, and there's some other good information in the book, some examples of scientific hypotheses and theories that really show the process of science. So have a good afternoon, and the next lecture will be on Chapter 4, where we talk more about Isaac Newton and some of the beginning ideas of physics and how we actually explain all of these things like Kepler's 3 laws of planetary motion.